Welcome to this explainer. Today, we're decoding one of the absolute coolest, most foundational mysteries in the entire history of physics. We're talking about Faraday's law of electromagnetic induction. So we're going to break down exactly how invisible forces can literally be harnessed to create real, tangible, flowing energy. It's wild to think about, but we're looking at a principle that, quite literally, powers our modern lives, yet it starts with a surprisingly, deceptively simple setup. Okay, let's dive into this. I want you to just take a second and ponder this exact question. Can a simple magnet actually create electricity without a battery? I mean, in our everyday experience, right, if we want to power our phones, turn on a flashlight, or run a motor, what do? We instinctively reach for a battery or we plug into a wall outlet. We're totally conditioned to believe that electricity has to come from a chemical reaction inside some battery or from a massive power plant miles away. But what if the raw materials for creating an electrical current were actually just sitting right there in the form of a basic, simple magnet and a piece of wire? No way, right? Well, let's see. To answer that, we've got to look at the evidence. And our evidence today comes straight from three absolutely crucial experimental observations made by the brilliant Michael Faraday. We're going to examine these visual clues step by step to figure out the mechanics of how electrical energy can seemingly be, well, conjured out of thin air. And look, these aren't just dry textbook facts. No, these are the actual physical clues that crack the entire case of electromagnetic induction wide open. So take a close look at the diagrams here on the screen, showing Faraday's actual experimental observations. You're going to see three distinct setups, labeled A, B, and C. In all of these, you'll notice we've got coils of wire, we've got magnets, and we have this little device labeled with a G. Now that G stands for a galvanometer. It's essentially a highly sensitive instrument used purely to detect if an electric current is flowing. Basically, if that needle on the galvanometer twitches even a little bit, boom, we have electricity. These three specific diagrams hold the exact secret we're trying to uncover right now. Let's see how this builds across the three scenarios. Let's start with setup A, our first clue. We see a bar magnet being physically moved towards a coil of wire that's hooked up to our galvanometer. And as that magnet moves, the needle twitches. A current is totally detected. Okay, now look at setup B. It's a very similar situation, but this time the magnet is kept perfectly 100% stationary, and the coil of wire is moved toward the magnet. And what happens? Again, the needle twitches, current flows. Finally, check out setup C. Notice there's no physical movement of a bar magnet here at all. Instead, a changing magnetic field is being produced by just varying the current running through a neighboring electromagnet. And guess what? Yep, the needle twitches yet again. Now, what's really fascinating here is the dramatic contrast between a stationary system and a changing one. Honestly, this is the key to the whole mystery. If you just take a magnet, place it inside a coil of wire, and just leave them perfectly still, absolutely no current flows. Literally, nothing happens. The galvanometer sits dead at zero. The current only flows when there's relative motion between the coil and the magnet, or when the actual strength of the magnetic field itself is actively changing. So stillness equals zero electricity. Change in motion, that equals flowing current. So I want to pause here for just a second and challenge you. Looking at those three setups we just went through, moving the magnet, moving the coil, or changing the current in that electromagnet, can you guess what the common denominator is in all three of these situations? I mean, we've got different moving parts, right? And in one case, we have no physical movement at all, just a changing electrical field nearby. So what is the single common thread tying all these events together? Well, the unifying factor, the real common thread in all three scenarios, is a changing magnetic flux. Now, think of magnetic flux as the amount of invisible magnetic field lines that are passing through the loop of our wire coil. In every single successful experiment Faraday ran, the magnetic flux going through that coil was actively changing over time. So whether the magnet was pushed closer, pulled away, or magnetically altered by an electromagnet, it was that state of active change in the magnetic environment that forced the current to flow. And this brilliantly illustrates the scientific definition of an induced current. When you hear that term, induced current, it simply means the current flowing in that coil entirely because the magnetic field passing through it is changing, often because of that relative motion between the coil and the magnet we just talked about. Notice, we didn't hook up a traditional battery. We essentially induced the electrons to move just by disturbing their magnetic environment. How cool is that? But solving one mystery almost always immediately presents another logical hurdle in science. We have to ask, what is it that fundamentally gives rise to a current in a circuit in the first place? Like, we know the action, changing the magnetic field, creates the current, but structurally, within the fundamental laws of physics, how is it actually happening behind the scenes? Think about your standard circuits for a second. They absolutely require a source of energy to physically push the electrons along. Usually, this energy is explicitly supplied by a chemical battery or, a plugged-in power supply. But since we clearly have a current being detected by the galvanometer in our coil, there must be an unseen driver present. There has to be a source supplying energy to the circuit, basically acting exactly like an invisible battery to make those electrons move. Well, Faraday realized this theoretical necessity too. He deduced that an induced electromotive force, or EMF for short, must be present in the coil. EMF is that driver. It's the necessary power source that gives rise to the induced current. By changing the magnetic flux, Faraday wasn't just, creating current out of thin air. He was actually generating an electromotive force, a voltage, right inside the wire itself. And that is what then pushed the current along. So the crucial point here is this grand, incredibly elegant conclusion known as Faraday's law. It states so simply and powerfully that a changing magnetic field produces an induced electric current. All of those experimental clues we looked at, the moving magnet, the moving coil, the varying electromagnet, every single one of them points directly to this foundational rule. You alter the magnetic environment around a conductor, and you will induce an electromotive force that drives an electric current. It's a total game changer. Which leaves us with a truly massive thought to chew on before we wrap up. If simply moving a magnet near a coil of wire induces an electrical current, how does this invisible force power the modern world around us? I mean, think about the massive turbines and power plants, hydroelectric dams, and wind farms. They are really all just giant soup-dip versions of Faraday's simple experiments. They're just spinning massive magnets and coils to constantly change the magnetic flux, which then generates the electricity that lights up our entire cities. It is an absolutely incredible piece of physics, and it all started from one simple, beautiful observation. Thank you so much for joining me on this explainer, and keep questioning the science around you.